Cruising at 35,000 feet over the Atlantic Ocean, the 228 passengers and crew aboard Air France Flight 447 flew into a massive, turbulent storm cell. Deep inside that storm, microscopic supercooled ice crystals rapidly accumulated on the outside of the aircraft, freezing over the plane's pitot probes, the small external sensors that measure how fast the jet is moving through the air. Look at this pitot tube diagram. Air enters to measure pressure. As ice blocks the intake, airspeed data instantly drops to zero. Without a reliable reading, the computers cannot function, immediately disconnecting the autopilot and autothrust. In less than a second, a temporary freeze of a tiny external sensor forced a startled, resting crew to manually fly a 200-ton airliner through the pitch black of a mid-ocean storm. When the autopilot disconnected, the Airbus A330 software automatically shifted into a degraded operating mode known as alternate law. In this mode, the aircraft strips away its fail-safe aerodynamic protections. This graphic shows the difference in those flight modes. On the left, normal software physically blocks a pilot from pulling the nose up to a dangerous angle. On the right, in alternate law, that hard boundary disappears entirely. The computer essentially threw its hands up. It handed over an unprotected, highly sensitive aircraft to human pilots who had spent thousands of flight hours relying along those invisible guardrails to keep them safe. The sudden blare of the autopilot disconnect alarm triggered the startle effect, a sharp cognitive freeze under unexpected stress. The junior pilot flying the aircraft gripped his side stick and abruptly pulled back. He kept the stick pulled back, forcing the nose of the plane up into a steep, sustained climb. The massive aircraft quickly began bleeding off the forward momentum it desperately needed to generate lift. Airbus cockpits feature unlinked sight sticks. If the pilot on the right pulls his control stick back, the stick on the left remains perfectly still. The experienced co-pilot had no physical way of feeling his partner was commanding a fatal climb. The crew was reacting blindly. Commercial airline pilots almost never practiced manual handling or recovering from extreme stalls at high cruising altitudes in their simulator sessions. Aviation safety experts later identified this exact combination: inadequate manual flying skills at high altitude, paired with a complete misunderstanding of the aircraft's degraded software state. The automation successfully masked the severity of the crisis. With hidden control inputs, contradictory alarms, and an environment devoid of outside visual references, the two co-pilots were effectively flying two completely different airplanes in their minds. As the aircraft lost its lift and began dropping out of the sky, a loud synthetic voice yelled "stall" through the cockpit 75 separate times. Incredibly, neither pilot ever acknowledged it out loud. This graph reveals a fatal logic trap. The stall warning shut off below 60 knots, assuming an error. Pushing the nose down accelerated the plane past 60 knots. The computer revalidated the data, reactivating the alarm, actively punishing the pilot's correct recovery action. Believing he was making things worse, he pulled the nose back up, which silenced the alarm once more. The machine's own programming actively punished the pilot for doing the right thing. Trapped in a deep aerodynamic stall with its nose pointed high into the sky, Flight 447 dropped out of the air, plunging into the Atlantic Ocean at 10,000 feet per minute. It took nearly 2 years to locate the wreckage, and over a decade of litigation followed. In a landmark 2023 trial, a French court ultimately acquitted both Airbus and Air France of involuntary manslaughter. For safety and engineering professionals, the disaster leaves a permanent lesson in interface design. When systems fail or degrade, alarms must provide operators with clear, unambiguous feedback, not paradoxes. On an organizational level, management cannot hold operators responsible for flawlessly executing emergency procedures if those individuals have never practically rehearsed them in realistic, high-stress conditions. Automation is a highly effective tool, but it will eventually fail. True systemic safety requires resilient operators who know exactly where the software's capabilities end and their own responsibilities begin.